So I'll explain attention is all you need 2017 paper from Google team. So all they explain is this was the introduction of transformer networks. So which has become the state of art for all almost all NLP tasks. What in this paper they were trying to say is they they were proposing you don't need any RNNs or CNNs for any encoding sequential information, which was considered important for NLP tasks. So the first problem they were solving with this paper is sequence to sequence problems or models. So where this applied sequence to sequence means you encoded n inputs and the model gave you m outputs. This what I mean is normally you know this you got this problem right?
Yeah, sentence is in English and then you translate it to French, which may be different line, different outputs, different words.
So that's what I meant. So the previous data parts before they published use LSTM or RNNs to encode it. So how they do is say suppose manage so what they do they use the embedding, find the embeddings of this. They pass it to a neural network. The networks give you a hidden state. They start with some kind of relationships. So then again they give this hidden state to the next word. They calculate x2 is same network. So what they do is then the final thing they get and feed it to a decoder network to predict the words. And again they use hidden state after following this to any other decoder to predict the probability. So this will be say the thumb, whatever word. This is back transition. So what they had was they had to traverse to the whole sentence, then compute a hidden state, then use that information to decode the words one by one. So what is the major problem in this is like once you want to compute this value, you only have the information which is passed on by this decoder and your output word. So most of the times you lose all the information and you are left with only this information, which is most of the times is not sufficient. One direct way is like each time in this H1 you can try to predict this word, but you will not encode the context of the full sentence. In that case, it will just be a meaning to meaning representation. So what this paper proposes is you try to, for each output prediction, the model tries to attend the inputs, how much weights is like a weight word, but how much weights it should give to each of the input words. Say for this word, a particular sentence might be more particular word might be more important for this translation. So the proposed model tries to attend the input for the output. Yeah. So the three advantages they propose in attention mechanism is like the computation per layer is minimized, and it can encode long range sentences well. Meaning, what they meaning is like if the in case of sequence to sequence, the information has to traverse a very long path. But if you use attention, that path is reduced to a constant. So the information need not travel larger distances. By that, it will not lose information. So these are the two main advantages of attention they propose. So and it was a transformer architecture. So you have input embedding. So the input embedding is your word embeddings. These are passed on to a push encoder because there is no way to encode the push-shell information except this, since they don't have any sequential or spatial feature extractors. And then you have a, they call it multi-head attention network. Then the output is added as a residuals and normalized. As it complete the program. So this part is the encoder part. So what happens here is the input embeddings are encoded with the positional information, and they are passed on to a module called multi-head attention. This module attends the input and passes on information which are added as residuals. Then a normalization happens on the data. Then it is passed to a feed-forward network, and again information is added as a residuals and normalization happens. So what this multi-head attention is, this is just the encoder part. There is also a decoder part. So you have your These are all H layers. Then they concatenate it. Then they suppose yeah. So these are some X-ray lighting which is good. So what I mean by this is, here you can see three types of information flow, three types of weights. So they are query, key, and value. Then they pass on to a module, which they call scale dot product module, and then they can concatenate information across all this and map it to the linear. So what this means is, they're trying to model the whole information into a set of key value pairs, and based on your encoded input, they are trying to find out which the queries which will satisfy your needed information, and they just have a lookup table which maps the queries to the keys, and they just give the values of the keys to them. They just pass on these values to the network. So how it happens is, they take this model I'm explaining. So what they take a inner dot product of query and the key. Then they take the softmax of that. Then they multiply the softmax probabilities with the values. So this is their whole attention. This is what they call attention. So this is a mathematical form. What this intuition means is, say these are vectors, right? All are vectors. So all are vectors pointing at different dimensions. So I'm putting in 2D. So what it does is, each are certain keys. So when you take a query and find the dot product, so the dot product is going to give you, this is also vector, dot product will give the maximum values if they are in the same direction, right? So the query will match to the keys which have higher values. Then they have, for each k values, they have a table for k1, v1, k2, v2, k3, v3. So this the corresponding value for this key is taken from this table. How they do is, so once you take a softmax, you get a different probabilities over all the values. So they just take a matrix multiplication, which is like a weight. You have weights for all the values. So you directly select the values which wants to be used by these queries. Typical example will be like, there are a lot of rows of certain information about a person. Say name is Saravanan, height is this, height is this. The query will ask what is the name. So the values. So when you apply this, it will give you the answer. So they have embedded this logic into this attention mechanism. So this is what they call attention. When you do multiple layers, they call it. So they use for I think 8 layers. So they just stack all the layers, and they have found that each layer is able to learn particular things about a certain language. Say, I'm not exactly sure, but they have found like certain things are able to represent vocabularies, certain nouns or something. So that is one multi-head attention. So like this, this is the encoder part. Then they pass on to a feed-forward network where it tries to add linear layers, uh, tries to build a function which maps these values and keeps it in a certain form. Then comes the decoder part. So the decoder also has the same configuration. Same multi-thread. So in the decoder, you will be expecting your output words, right? So output embedding means the words which were given at a particular inference. So what time? This is important. Say AI is awesome, and you're trying to predict in so this is the output embedding. So and you're trying to predict this word. So this is one sample for attention network. Whereas in a RNN, you will feed the full sentence as a sample, right? You will try to model the full sentence, but for attention, you can pass it like each step is like a sample for it. So you pass this full information and you want to predict this. So this becomes the output embedding, this becomes the input embedding. This is fed into the encoder network, this is fed into the decoder. So this also has 3 edges. It also has a feed forward network. Why do you think it has to be?
In that attention, I think there is a divided by square root of pk.
And that is just a normalization. You just normalize it. After this, they have the suffix. So they try to pass this model the output embedding also in the same form and give this information as a value which, so this has queries and keys, the values is given by this. Then they again do a feed forward network, model the function, then try to predict the probabilities. That's it. This is key value. So one more information is there will be also having a mask somewhere here in the scale dot product so that they will not predict the next sentences also. So the mask is saying that you need to only cover this.
So you have the sentence AI is awesome and the task is translation, let's say. So you have 3 input vectors which you input here. What do you get at the end of the encoder in this case? Like at the end of
This
I mean, do you get a vector or I'm just confused? You get a vector. So what are the output embeddings actually? I don't understand.
same for each in the domain transfer language you will have a embedding, right? So that embedding.
Okay.
You need to have embeddings for both the languages. So for the embeddings for this exact word, So whatever you had previously predicted also you have to give in to predict the next one.
Mm.
So that is.
And they mask the other one.
Mm.
So in the positional encoder, what is positional means actually?
So what they do is you have to somehow encode the positional information, right? But there is, so how they do is they take two waves, a sine wave and a cos wave, right? Okay, so okay, consider two waves with different frequencies, three waves. So what they do is for the first word they take this information as this value, this value, this value. They form a binary value and try to add it to this. So what it gives is like a unique um, place in position for that word. So the next word will be encoded with this, this, this. So what they mean is, say suppose a word is high here and it's low here in the long range. This is low frequency wave, right? So in the low frequency wave, if it is too separated by this much distance, it knows that they are very far. Whereas these are also same, these are also same, but in the high frequency wave they are separated. It knows like the words are near.
The conversion to binary meaning?
They encode this and multiply this. I'm not exactly sure. This is a different way.
It's actually pretty interesting.
This one.
Huh.
Okay, I'll try to read it.
The key query are learned matrices.
Everything is done. They are 5 to
No, I think they are more than
5 to 11.
the key query vectors.
All are same.
No, I think they are lower. I think that's 64. 64 or something.
I'm not sure. I think key and value are 64. The table they will have key and value is 64. The model is 5 to.
In the example that you were giving, that supposingly you have some text where there's information pertaining to you, your name, height, whatever. So query would be what's your name or what's the name?
Query would be like I need name.
Okay. What would be the key and value exactly?
Key is the name.
Okay.
Query is asking. It's like a search. Like I need this.
Mhm.
The mapping table gives you that.
Okay, so determining the key and then the
That
value.
is what attention is, right? You give assign particular weights,
Mhm.
so it just picks the gives more weightage to that less weightage.
Okay.